As we move into the next chapter in Math 119, we're going to deal with a topic called polynomials. Polynomials are a little bit more complicated function than we dealt with linear functions in previous chapters. And so we're going to start out today with an introduction, just kind of getting a feel for the terminology we're going to use for polynomials. And then we'll do some very basic, in this video or in the next video, we'll talk about some basic operations we can do with polynomials, okay? So we'll start out today just with some basic definitions. First thing is, what is a polynomial? What am I talking about? Okay, so a polynomial by definition is going to be any algebraic expression where you're adding or subtracting terms together, and each of those terms has to have a variable with a power that is a whole number. So the power could be 0, 1, 2, 3, 4, 5, 6, and so on, okay? And so that's really the basics of it. So you have to have terms where the variable powers are whole numbers. So it's an algebraic expression with one or more terms where the variables have whole number exponents. And of course, whole numbers are 0, 1, 2, 3, and so on, okay, up to infinity, right? So there's an endless number of whole numbers there. Okay, so that's just your general definition. I'm sure this definition doesn't match your textbook perfectly. I'm just writing up there some of the key features, okay? Okay, so a couple examples of polynomials. You might see things like 2x minus 5. This is an example. It's actually a linear function, but it is an example of polynomial as well. Notice that in this example, there's two terms, 2x and negative 5. Okay, those are the two things being added together. In the first term, there is a variable, and its power is 1, its exponent, because it doesn't have it doesn't have one written in there. Okay, so it's understood to be 1. The 5 technically has a variable and a power as well. It's just not written in. Remember that anytime you have something raised to the 0 power, that expression is really just 1, right? So you could think of this as 5 times x to the 0, because x to the 0 is 1 and 5 times 1 is 5. So it doesn't change anything to add that x to the 0 or to multiply by the x to the 0. And because the variable then has a 0 as the power, which is a whole number, it still satisfies the definition of a polynomial, okay? Now we don't typically write that in. In fact, we usually don't even really consider that it's there. Okay, so we don't show it, but it is in some sense, and so so this term on the end still satisfies the definition of a polynomial. Okay. Another example you might see, something with some larger powers, something like 3x squared minus 8x plus 7. Okay, here I've got an x squared term, so power of 2, power of 1, and a power of 0 again. Okay. You may also see things with multiple variables. So we can have polynomials that have 2 or 3 variables in the same expression. So you could have like 15xy to the fifth minus 4 x to the seventh plus 17 y squared. Okay, and so this example, I've got three terms with two variables. One of the terms has both the variables, the other terms each have one of the variables. It doesn't matter. Again, as long as your exponents are all whole numbers, so 0, 1, 2, 3, and so forth, then we have a polynomial. Okay. The exceptions, the things that are not polynomials, are things that where the exponent is not a whole number. If you had negative exponents, that would end up creating a variable in a denominator when you move it around. So if I had something like 3x to the minus 4 power plus 7, well, that negative 4 is really 3 over x to the 4th plus 7, right? When you use your exponent rule for negative powers. And these things are not polynomials, okay? So the ones I'm writing in red right now, these are not polynomials. Okay. In addition to negative powers or things where variables are in a denominator, you may also see variables under a root, like the square root of x. Okay. And the reason that this is not a polynomial, we'll learn in a later chapter in this course, is that roots are actually fraction powers, like x to the 1/2. Okay, so we haven't learned this yet, but we will. And so for this reason, these fractions don't fit into the list of whole numbers, so this would not be considered a polynomial. Okay. There are many other types of functions that are not polynomials that we will be discussing later in this semester. But for right now, these are just a couple of examples. Just know that as long as the powers are nice whole numbers, we've got a polynomial. Okay. Now these polynomials have very important parts to them, and I'll be referring to the different parts. With different terms, okay, different terminology. And it's going to be important for you guys to know the terminology and to know the language, because so you can understand what I'm talking about, really. So in each of these, we have the idea of terms, right? We talked about that, and you guys know what terms are. They're the parts that are added or subtracted. But what I really want to talk about is a specific type of term called the leading term. Okay, actually, before I get to the leading term, that's kind of I need something else. We're going to talk about the degree of the terms. Let's do that first. Each term has a degree, and it happens to be the sum of the powers in that term. Okay, so it's the sum of the powers in that term. Now, when you have a polynomial with only one variable, those are easy. You just take the power from that variable in the term. So, for instance, in this first example, the degrees for 2x minus 5, the degree of the terms is 1 for the first term because that's the power on the x. And the degree for the second term, it doesn't have a variable, but it really does, remember, it has a variable to the 0 power. So we have a 0 degree on that one. Okay. If you don't see a variable, we call it a degree of 0. For the second one here, 3x squared minus 8x plus 7, the degrees of the term are 2, 1, and 0 because those are the corresponding powers on the variables. 2, 1, and 0. Okay. In this last example here, 15xy to the 5th minus 4x to the 7th, 17y squared, we do in this first term have to add together the powers. Remember, it is the sum of the powers if you have more than one variable. So here I have a power of 1 in 5, so this becomes a 6-degree term. This one has 7, and this one is 2. Okay? So again, when there's only one variable in the term, you just use the power on that variable. If there are more than one variable, you have to add those powers together. All right, so now that we know the degree of the term, there's another definition here called the degree of a polynomial. The degree, now I'm going to have to start moving some stuff up. The degree of the polynomial itself is the largest of all the degrees of the terms. Okay, so I'll write that definition up here. Degree of polynomial is the largest of the degrees of the terms. Okay, so it's the largest one. So in this first example, the degree of the polynomial is going to be 1, because that is the largest of the degrees. In the second one, the degree of the polynomial is 2, because that's the largest. And in this third one, the degree of the polynomial is 7, because that's the largest degree of all the terms. Okay, so that should give you an idea then, based on those examples, how to find those degrees. Okay, so you've got the degree of the term, it's the sum of the powers in that term. The degree of the polynomial is the largest of all the degrees of the terms. Okay, now we have a couple of extra definitions I want to talk about. One is called the coefficient. And we've talked about coefficients before, but I'm going to give them a little bit better definition. The coefficient is going to be the numerical factor in a term. Okay, it's the numerical factor in a term. So in each of these terms, or in each of these polynomials, the individual terms have a coefficient. Maybe I'll write those in here. Let's get rid of this couple lines. Keep the original polynomial. So in these polynomials, the coefficients are going to be 2 for the first term. And now I do want to make a note, the constants there on the ends, I don't believe fall into the category of a coefficient. Let me just double check on that. Oh, it is. Okay, we do consider it. So the 5 is going to be considered, actually the negative 5, is going to be considered a coefficient according to your textbook because it has technically the power of 0, x to the 0 attached to it. And so it is considered a numerical factor in the term. Okay, so the constants are included as a coefficient according to the definition in your textbook. So therefore, in the second polynomial 3, -8, and 7 are your 3 coefficients. And in the last polynomial 15, -4, and 17 are your 3 coefficients. Okay. Now the coefficient that appears on the largest degree term is called the leading coefficient. Okay, so leading coefficient is the coefficient on the term with largest degree. Okay, so it's the coefficient on the term with the largest degree. So in each of these examples again, the leading coefficient, I'll abbreviate coefficient there, is going to be 2 for the first one because that's the coefficient on the largest degree term. This one will be 3 because it's the coefficient on the term with the largest degree. And here, the term with the largest degree is the middle term here with the 7. So the leading coefficient is -4 on that one. Okay, so the leading coefficient is always going to be the coefficient on the term with the largest degree. Finally, the expression I was going to get at the beginning is the leading term. The leading term of a polynomial is the term with the largest degree. Okay, so I'll give you a definition here. Leading term is the term with largest degree. And so in each of these examples, again, the leading term is that, and this first one is 2x, and the second one is 3x squared, and in the third one here it's -4, oops, like that, inline, -4x to the 7th. Okay, so again, those are the terms with the largest degree in the polynomial, all right?